I, Dr.S.Pethanachi Selvam, Head and Associate Professor, PG and Research Department of Mathematics, SFR College for Women, Sivagasi. Today we are going to see the section Linear Transformation in Linear Algebra. Already two sections have been covered. Now here it is an important section in linear algebra, homomorphism or linear transformation. Let us see the concepts, introduction, applications, definitions and examples in this video. Before entering the concept, which areas this linear transformation is applied? Linear transformations are commonly used in image processing tasks, that is, scaling, rotation and translation of images can be achieved through linear transformation. Another application, modeling of 2D and 3D animation, where object size and shapes needs to be transformed from one viewing angle to the next. Third application, it is in number theory using the concept of linear algebra transformation. It is applied in various encryption and decryption algorithms. Now we can see how the definition is framed. What is the idea behind for defining this linear transformation? A transformation achieved by matrix multiplication. Usually matrix multiplication can be done by the two matrices. The first matrix is the number of columns in the first matrix equal to the number of rows in the second matrix, means we can multiply. That is the rule for multiplication. Here also in R3, that is a three-dimensional space, we are taking a vector which is of size 3 cross 1 x, y, z. Multiply the left hand side of this vector by a 2 cross 3 order matrix A. Here I am taking 1 2 0 2 1 0 matrix. Now here I multiply this matrix left side of the matrix of the vector in R3. Here you obtain the resultant product of the vector, it is of size 2 cross 1, that is x plus 2y 2x plus y, which belongs to R2. Now we can see that we have taken a vector in R3, the resultant vector is in R2. Here if we give any of the choice of x and y, the vector in R3 is transformed into the vector in R2 by the matrix A. This is the basic idea to define a function which takes vectors in R3 and delivers new vectors in R2. In this case, that function is multiplication by a matrix TA. In fact, this transformation, that is this matrix transformation, is simply a linear transformation. Mathematically, we are using these words in algebraic structures like groups and rings. Now we can formulate this concept of homomorphism or linear transformation for vector spaces also. Basically, we remember that always both vector spaces are defined over the field only, we can define linear transformation. Here mathematically the definition is like this. Taking a map between the vector spaces, V and W be the vector spaces, and the mapping F is called a linear transformation if it satisfies two conditions, T of U plus V equal to T of U plus T of V, T of alpha U equal to alpha into T of U. For all vectors U and V belongs to the vector space capital V and scalar alpha belong to the field F. We can define the same definition in another way, that is, we can frame it as a theorem and then give a proof. Suppose we have two vector spaces. The mapping T between the vector spaces is a linear transformation if and only if T of the scalar sum of the scalar products alpha V1 plus beta V2 equal to alpha T of V1 plus beta T of V2 for all vectors V1, V2 belongs to the vector space in the domain capital V and alpha, beta are scalars in the field F. You assume the first part. Suppose T from V to W is a linear transformation. We have to prove the part as alpha V1 equal to. Then you take two vectors T of V1 comma V1 plus V2 equal to T of V1 plus V2 by definition, and T of alpha V1 equal to alpha into T of V1. Then you take the left hand side T of alpha V1 plus beta V2 by applying the concept. T is a linear transformation. We can split up into T of alpha V1 plus T of beta V2. Then by using conditions 1 and 2, we can get the result. Therefore, we say that the first part is proved. Converse part, you assume the condition T of alpha V1 plus beta V2 equal to alpha T of V1 plus beta T of V2. We prove that T is a linear transformation. That means we have to prove the conditions addition and scalar multiplication. Take alpha equal to beta equal to 1 in the assumption, we can get the first condition. Choose beta equal to 0, then we get T of alpha V1 equal to alpha T V1. Therefore, here we say that the two conditions of the definition is satisfied, hence T is a linear transformation. Therefore, we have derived the equivalent definition for linear transformation. Now, we can see the simple examples and then which function will be a linear transformation and which one is not a linear transformation. Here 6 examples are given. The first easiest example is if you take an identity map or zero map between the vector spaces, identity map images goes to the same element. So, I of V equal to V, and zero map mapping every element to 0. That means I is 0 of x equal to 0 and 0 of x1, x2. Any element if you take from the domain, image will be equal to 0. Clearly, both transformations, both mappings, identity map and zero map are clearly homomorphisms, or other words, we can say that it is a linear transformation. Then second example, we consider the vector spaces. Both domain and codomain have the same vector space R3 over a field R. Here the image is defined as T of A, B, C. That is, here in R3, every element is a 3 tuple. Here T of A, B, C, image value will be equal to A 0 0. Here using this definition, we have to prove that the mapping T is a linear transformation. Here you can apply the theorem and then we can prove the result. Take 2 elements from the domain R3. So, each element is a 3 tuple A1, B1, C1, A2, B2, C2. What are the images? Here the images of V1 as A1 0 0, image of second element is A2 0 0 by definition. Now you can apply the condition of the theorem T of alpha V1 plus beta V2, then simply multiplication each element coordinate by alpha, then apply the definition, you can get the result alpha A1 plus beta A2 comma 0 0. Here we can split up into 2 parts, we can get it alpha T V1, beta T of V2. Therefore, by theorem we say that T is a linear transformation. Similarly, if you consider the mapping, the domain having the n tuple R power n is a vector space and the codomain is also the same vector space. The images are taken as T1, here the mapping T of, here there is T of A1, A2 etc. AN. The image will take the first coordinate element as A1. We prove that this mapping is a linear transformation. As usual, we have to take 2 elements from the domain R power n, each one having n tuples A1, A2 etc. AN. Second element having coordinates that is B1, B2 etc. Bn. What will be the images in the codomain? T of V1 takes the images A1, T of V2 takes the first coordinate images P1. Then apply the theorem, take the left hand side T of alpha V1 plus beta V2, add the 2 elements, corresponding coordinates are added, you can get the image will become alpha A1 plus beta B1 by definition, because other coordinates not lie in the image. Then it can be written as alpha T of V1 plus beta T of V2. Therefore, here also the condition is satisfied. The given mapping T from R power n to R power n is a linear transformation. Similarly, if you define a map in the form T of A1, A2 etc. AN equal to A1 0 0 means, similarly we can also prove the result that it is also a linear transformation. And then the next example, you have taken the mapping V is a domain and the codomain as the quotient set V by W. Therefore, the images will become T of V equal to the codomain images will be of the form W plus V. For every element V belongs to capital V. We prove that this mapping is a linear transformation. As usual, take two elements from the domain capital V and one scalar. That is, here we can prove the result, that is by definition also as well as by theorem also. Both conditions are here satisfied. T of V1 plus V2 equal to, by definition, W plus of V1 plus V2. By coset definition, we can split up into W plus V1 plus W plus V2. Because V1, V2 belongs to capital V means T of V1 equal to W plus V1 and T of V2 equal to W plus V2. Therefore, addition is satisfied. Similarly, scalar multiplication by the coset definition, W plus alpha V1 can be written as alpha into W plus V1, that can be written as alpha T of V1. Similarly, you can apply the definition also. We can simply prove the result that this function is a homomorphism. The name for this mapping, V to V by W mapping, is called as a natural homomorphism. Then another example, if you take the domain V is a vector space and it consists of the set of all polynomials of degree less than or equal to n. The coefficients of the polynomials are from the real number system. This set contains the zero polynomial also, and here you prove that the domain T from V to V defined by the T of f of x image is derivative of the polynomial. We have to prove that T is a homomorphism. For that, as usual, you apply the concept of, instead of elements, two elements, we are taking the domain, the elements are polynomials. Take two elements f of x and g of x from the domain capital V. The images will be as a derivative of that polynomial. Therefore, it can be split up into d of, derivative of two functions can be split up into derivative of the first polynomial alpha f of x and the derivative of second polynomial beta g of x. Apply the definition, you can simply get the result alpha into T of f of x and beta into T of g of x. Therefore, here also T is a homomorphism. And then the next example says, if you define a function between R, V3 over R to R, take an element from V3 over R, every V3 over R equal to R power 3. Here the element is x, y, z. The image will be in the real number system if you define as x square plus y square plus z square. Here the condition fails, that is addition is not satisfied. Therefore, it is not a linear transformation. That is, take two elements from the domain, each one is a 3 tuple, and here the images will be x1 square plus y1 square plus z1 square, and the image of second element will be x2 square plus y2 square plus z2 square. Then addition of two elements v1 plus v2 will be, the corresponding coordinates are added. You can get x1 plus x2, y1 plus y2, z1 plus z2. Apply the that is addition condition T of v1 plus v2. Then by definition you can get it the square of each coordinate. When you expand it, you won't get T of V1 plus T of V2. So, addition condition fails. By definition, we say that T is not a homomorphism. And then we can see some important results in the homomorphism. The collection of all images T of V belongs to W. It is a subspace. V is the domain and W. V and W are vector spaces and T be a homomorphism between the vector spaces. We prove that the image of the whole domain, it is also a subspace in W. The image set T of V will have the set, it will be of the form T of small v, where V belongs to capital V. First of all, to prove the subspace, we have to prove that is, it should be a non-empty subset satisfying the addition condition, and that is a scalar multiplication means addition under, that is two vectors are added. The same vector also belongs to the set T of V means addition is closed. And next one, scalar multiplication is also belongs to the set T of V means we say that a non-empty set satisfying the closure property and scalar multiplication means we say that the set is a subspace. Here the first condition, to prove closure, we are taking two elements W1 and W2 belong to the set T of V. every element in T of V is of the form T of small v, where every element V1 belongs to capital V. Now we are taking W1 and W2 in T of capital V. So each element will be of the form W1 equal to T of small v1 and W2 equal to T of small v2. Here hypothesis is T is a linear transformation. So apply the hypothesis, we can get the condition by definition T of v1 plus v2 equal to T of v1 plus T of v2 and T of alpha v1 equal to alpha into T of v1. Our aim is T of V is a subspace of capital W. Clearly T of V is non-empty. In the first step we have noted, because V is a vector space means under addition 0 belongs to V. Therefore clearly T of 0 belongs to the set T of V. Thus we say that T of V is a non-empty subset of W. Next we prove the addition W1 plus W2, which is equal to T of V1 plus T of V2. Since T is a linear transformation, we get T of V1 plus V2 and T of V1 plus V2. Here V1 V2 belongs to capital V means addition is closed in V. So V1 plus V2 belongs to capital V. So we say that T of V1 plus V2 belongs to T of V. Thus we say that W1 plus W2 belongs to T of V. It is given in condition A. Also similarly alpha W1. Alpha W1 can be written in the form T of V1 by condition 2, that can be written as T of alpha V1. Now small v1 belongs to capital V. Since V is a group, clearly alpha V1 belongs to V. So that T of alpha V1 belongs to T of V. So that we say that alpha W1 belongs to the set T of V. Now from the three conditions, T of V is non-empty, and by A W1 plus W2 belongs to T of V, by B alpha W1 belongs to T of V. Now T of V is a non-empty subset satisfying closure and also scalar multiplication. Thus we say that T of V is a subspace of W. Then next important theorem plays an important role in linear algebra. Suppose take two vector spaces over the same field F, and we can say that the collection of all homomorphisms is also a vector space over the same field. In mathematical notation, we denote it by L of V, W. It contains the collection of all homomorphisms from V to W. We prove that this collection is a vector space over F under the operations addition and multiplication, which is defined as F plus G of V equal to F of V plus G of V and alpha F of V equal to alpha F of V. Here first we prove that L of V, W is an abelian group under the operation plus. First we prove that addition is closed. As usual, we have to take two elements from the set L of V, W, and you prove that the addition of two elements also belong to the set L of V, W. Here the set consisting of only the homomorphism, we take two elements as homomorphisms. We are taking two homomorphisms F and G and corresponding elements. We prove that F plus G belongs to L of V, W. That means F plus G is also a linear transformation. And to prove this one here, as F and G are linear transformation, it satisfies equations 1 and 2 because addition and scalar multiplication is true by definition of linear transformation. To prove F plus G is a homomorphism, because if we prove like this, then clearly we say that F plus G belongs to L of V, W. So take F plus G of the first condition addition V1 plus V2. That means F of V1 plus V2 plus G of V1 plus V2. As F and G are homomorphisms, we can separately split into two parts. Therefore, we can combine F and G. Therefore, you get F plus G of V1 plus F plus G of V2. Similarly, the scalar multiplication F plus G of alpha V1, by definition F of alpha V1 plus G of alpha V1. By condition 2, we can take alpha, that is by previous part, we have the definition. that is alpha into, by using definitions 1 and 2, we can say that alpha f of v1 plus g of v1, close the bracket. Then alpha into f plus g of v1. Therefore, here it is the image. Therefore, it is all f plus g belongs to L of v comma w. That means it will become a homomorphism. Therefore, it satisfies the condition. So, we say that plus is closed. Here plus is closed between two linear homomorphism. Plus is clearly associative because it plays for three homomorphisms f, g and h. Therefore, as addition is defined on L of v, addition is associative as well as commutative because f plus g plus h of v equal to f plus g plus h of v. We can change the bracket, we can prove the associativity, and addition f plus g is true means g plus f is also true. That means the images will be equal. Homomorphisms, the mappings are equal, images are equal. So, we can say that f plus g of v equal to g plus f of v. Plus is commutative. Next, we can prove that identity. If we take a homomorphism f and take an identity element as a map as 0 map, a 0 map is defined as f of v equal to 0. Clearly, this function is the additive identity. Every 0 map is the additive identity of a homomorphism f belongs to L of v comma w. Similarly, if we take a homomorphism f minus f, its inverse image is the inverse of f because inverse element is also a homomorphism. Minus f of v equal to minus of f of v. It is the additive inverse. Thus, we have proved the addition is closed, associative and then commutativity, and every element in L of v comma w has additive identity as well as inverse. Thus, we can say that L of v comma w is an abelian group under addition. And next we prove scalar multiplication. First we prove that alpha f is a homomorphism. Then only we can say that alpha f belongs to L of v comma w. To prove it is a homomorphism, we have to prove the addition and scalar multiplication. Apply the map alpha f on the addition v1 plus v2. Then alpha f of v1 plus alpha f of v2. Take by definition alpha into f of v1 plus f of v2. Then we can say that alpha into f of v1 plus alpha into f of v2. Similarly, the scalar multiplication can be written as alpha f of v1 equal to, that is wrongly defined, that is alpha into beta can be omitted, then beta is wrongly entered, alpha into f of v1, that can be written as, take alpha outside, you can say that f of v1. So, alpha f belongs to L of v comma w. Now, we can verify the remaining 4 axioms of the vector space. The first condition is alpha into, usually the elements means u plus v equal to alpha u plus alpha v. Here the elements are, that is a homomorphism. So, you take the two homomorphisms f and g. So, the conditions will be alpha into f plus g equal to alpha f plus alpha g, and alpha plus beta f equal to alpha f plus beta f, that is omitted. Here you can add it, alpha f plus beta f. And the third condition is beta f equal to, that is alpha into beta f equal to alpha beta of f. One alpha is missed here, and then that right side also one f is missed, and 1 into f equal to f. To prove the conditions, the images are equal because all are mappings. Mappings are equal. We prove the first 4 conditions, each one defines it is a mapping. To prove mappings are equal, the images are equal. So, we prove that take an element from the domain v belongs to v. Then you apply the first left hand side, alpha f plus g of v equal to alpha into f plus g of v. Because f plus g is a homomorphism, we can split it into f of v plus g of v. And then you can take the scalar into the each element, alpha f of v plus alpha g of v. Because alpha f is a homomorphism, we can take it outside. So, you can get alpha f plus alpha g of v. So, both sides are equal. So, mappings, every element, the images are same, the mappings are equal. Similarly, we can prove second, third and fourth conditions as alpha plus beta f of v equal to alpha f plus beta f of v. and third condition is alpha into beta f of v equal to alpha beta of f of v. Therefore, the fourth condition obviously true, 1 into f of v equal to f of v. That means we have proved all the axioms of vector space under scalar multiplication. Thus, we have proved that the set, the collection of all homomorphisms form a vector space or otherwise linear space over a field F. Then some more special mappings according to this definition. Suppose we have two vector spaces over the same base field F, means if a linear transformation is 1 1, then the transformation is called as a monomorphism. If a linear transformation T is onto, then the homomorphism is said to be an epimorphism. If a homomorphism is both 1 1 and onto, then the homomorphism is called an isomorphism. Suppose two vector spaces are isomorphic, means then there exists an isomorphism between the vector spaces V and W. Then another important mapping is a linear functional. When does a homomorphism to be a linear functional, means your mapping, your transformation T from the domain V to the any field F is called as that linear transformation from V to F is called as a linear functional. Here up to this, the section transformation is completed. Next one, using this linear transformation, we introduce the very important concept in algebraic structure that is called as a kernel. What is meant by kernel of a linear transformation? It is also just a mapping. What will be the images in the codomain? Okay, only we are considering the zero element of the codomain, collection of all. For what elements of V, we can get the image to be 0. That collection of element set is called as kernel. Suppose you take a linear transformation between the vector spaces V and W. Kernel T is the collection of all elements from the codomain. Here those images will be equal to the 0 element, that is an identity element in W, means that collection is called as a kernel T. Here we can see some more examples of kernel T. Here the first example, we can see that the first example is identity. First example, the mapping, 0 mapping, because T of V equal to 0. This is a linear transformation. Here if you define kernel T, means the image is defined as every element in the codomain has the image 0 in the codomain. So, all the elements of V will belong to the set kernel T. So, we can say that kernel T equal to V, because image of every element in V takes the value equal to 0. Now, the next example, we consider the vector spaces and the mapping is defined as identity mapping. T of V, every element in V takes the same image as V. It is also a linear transformation. Here if you find the kernel T, every element in V, the image will be equal to 0. So, totally the set will be 0 only. Okay. Now, the next one is kernel for the some more elements. The domain is V4 over R to V4 over R. The images are, except the first and third coordinate, all other elements to be equal to 0. If you find kernel T, by definition, it is a 0 element, as in V4, it is 0, 0, 0. So, each coordinate will become 0. So, kernel T will take the ordered 4 tuple 0, x2, 0, x4. Similarly, in V3 over R, in the next example, we can prove by the definition itself, you can get the set as 0, CC. And the next result is, T is a linear transformation. We prove that T is 1, 1 if and only if kernel T is 0. Okay, singleton set 0. You take the hypothesis T is 1, 1. We prove that the set kernel T equal to 0. That means every element in the set kernel T is 0, means kernel T will become singleton set 0. So, for a particularly we take some other element V belongs to kernel T. By definition T of V equal to 0. T of 0 can be written as T of 0, which implies by T is 1 1 we get V equal to 0. So, the element we have taken one element from kernel T, that element will become 0. This is true for every element in kernel T. If you take any element, then we can get kernel T equal to 0. Now, next one converse part, assume that kernel T is singleton set 0. To prove T is 1 1, so assume the condition T of V1 equal to, the images are equal, then the elements are equal. But usually the definition, every element in the domain has distinct elements in the codomain. Here also we have taken the opposite part. Suppose the images are equal, the elements in the domain are equal. So, in applying the T is linear transformation, we can prove that T is 1 1. Then the very important and last theorem in this section is fundamental theorem of homomorphism. Here we are taking an epimorphism. Epimorphism means it is an onto homomorphism between the vector spaces V and W over a field F. You prove that kernel T equal to V1 is a subspace of V and V by V1 isomorphic to W. So, first we prove that kernel T is a subspace. Next we prove that there exists an isomorphism between the domain V by V1 and W. Here you can see the first part. Kernel T is a subspace means by applying the theorem, previous theorem, T of alpha U plus beta V. Also we prove that that is condition addition and scalar multiplication. Here T of 0 equal to 0 means 0 belongs to, the one element belongs to kernel T. So, kernel T is a non-empty subset of V. To prove kernel T is a subspace, it is enough to prove that alpha U plus beta V belongs to the set kernel T. That means it is enough to prove that T of alpha U plus beta V equal to 0. For all elements UV belongs to kernel T and scalars alpha and beta. You take two elements U comma V belongs to kernel T, then by definition of kernel T, both elements having images 0 and 0, that is taken as equation 1, and take the condition T of alpha U plus beta V. T is a homomorphism. We can take alpha outside, we can split up T of U plus T of V. By condition 1, both values are equal. So, T of alpha U, image of that value equal to 0 means alpha U plus beta V kernel T. So, by theorem we say that kernel T is a subspace. Next one, you prove the isomorphism. V by V1 isomorphic to the vector space W. That means we have to prove the existence of an isomorphism between the vector spaces. You define a map that function as pi and it is defined as the domain elements V by V1. It is a quotient set. The element will be of the form V1 plus every element from V. So, V1 plus V. For all V in V, the image is in W. Here W belongs to T from V to W. So, every element in W will be of the form T of V. So, the image is defined as pi of V1 plus V equal to T of V. First the map is well defined, then you take the elements in the domain are equal, the images are also equal. So, you take the two elements by left coset condition, we get it V equal to V1 plus W, then you take T on both sides because T is an epimorphism. 1 condition is true, so we can apply T on both sides, T of V equal to T of V1 plus W. Since T is a homomorphism, we can split up T and T of V1 belongs to kernel T means T of V1 0, that is W. So, we can say that T of V means pi of V1 plus V equal to pi of V1 plus W. So, we say that pi is well defined. Next one, pi is 1 1. The images are equal, the elements are equal. Here you prove the result T of V equal to T of W, which implies T is a homomorphism. We get T of V minus W equal to 0. By definition, V minus W belongs to kernel T. Here kernel T is taken as V1. That means V minus W belongs to the set kernel T, that is V1. So, V1 by left coset condition, V belongs to capital V1 plus W. By using the property V1 plus V equal to V1 plus W, then we can prove that it is 1 1. Next we go to onto condition, take an pre-image, take an element in the codomain W and we prove that there exists an element in the domain V by V1. Here W belongs to W means W is the image in W, we have the map T from V to W. So T is onto, it is an epimorphism. So there exists an image, pre-image element in V satisfying the condition. Now by definition T of V means pi of V1 plus V. So for every element small w in capital W, a pre-image exists V1 plus V belongs to V by V1. Thus pi is onto. Next one, homomorphism. We prove addition and scalar multiplication. Take two elements from the domain. One element is V1 plus V, another element is V1 plus W. Two distinct elements taken from the domain V by V1. Apply the addition condition, add the two elements V1 plus V plus V1 plus W. Apply the mapping pi of V1 plus V2, that is equal to V1 plus V plus W. By definition T of V plus W, as T is a homomorphism, it can be split up into T of V plus T of W. That means pi of V1 plus V plus pi of V1 plus W. Similarly, we can prove scalar multiplication alpha into V1 plus V. Apply the T is a homomorphism and definition of the mapping pi, you can get pi of alpha V1 plus V equal to alpha into T of V1 plus V. Now the two conditions of homomorphism are satisfied, thus pi is a homomorphism. We have proved that the map pi is well defined, 1, 1, onto and homomorphism. Thus we say that pi is a isomorphism. That means V by V1 isomorphic to W. Thank you.